Johnny back here again. Wanted to continue our discussion. We started talking about mathematics for machine learning and for artificial intelligence, and I wanted to come back to that and show you a new way of looking at it. Apart from mathematics, cooking, old cars, aeroplanes, books, I like history. I've always been fascinated by history, and so I'm going to kind of take us back in time. Actually, I'm going to start looking at some mathematics that was written about 2,000 years ago. It was written about during the time of Christ by a chap called Hero of Alexandria. I first became acquainted with Hero was I used to go and visit my grandmother in Norfolk, and this book was on her bookshelves, and actually she had three. It was a set of three. This is an encyclopedia called Junior Science, and it really smells like an old book. It's just wonderful. Published in 1950, yeah, I used to love reading this. It has a little bit of mathematics in it. But it's wonderful, black and white pictures of steam engines, and when it talks about electronics, it's only valves and things like that, and cutaway drawings of aeroplanes and engines. And anyway, there's a section, there's a chapter which is called the introduction of the steam engine, and it mentions this chap called Hero. It says, roughly half a century before Christ, the celebrated Greek inventor Hero devised a mechanism for opening and closing altar doors. He was an engineer, a very famous engineer, but he was also a mathematician, and he published mathematical texts that survive to this day, 2,000 years old. Amazing. So I went to Wikipedia, and they had this to offer me on Wikipedia Commons. That's what he looked like, rocking the beard there, Hero. So what I want to talk to you today about is an algorithm that he wrote about for calculating square roots of a number. Now, you might ask yourself, why would I want to talk about a 2,000-year-old algorithm? Answer is simple, and it comes in two parts. It embodies the essence of machine learning. We take a guess for an answer. We don't know the actual answer, but this algorithm allows us to infer, if we have a guess, it tells us a way to get a better guess. And if we can make successively better guesses, we will arrive at a solution. That, my friends, is machine learning in a nutshell. It's the way that we train our machine learning and artificial intelligence models. We don't know the answer. We don't know the way to get a solution. But if we can find a direction, a path that will get us closer to the right answer, and we take a small step in that direction, and then we look around again and think, is there a different path? And we just keep on getting down this path, we will get to the solution. And we will come on to that, and I'll show you this working in some sophisticated machine learning models. But for now, let's just watch that actually happening with Hero's algorithm. The second point, which I think is very, very topical, very up to date, this algorithm shows that we can get a useful answer with very rough mathematics, crazily rough mathematics, in fact, and I'm going to kind of take an extreme case and show you that it still works whether we completely abuse the mathematics or not. Why is this important? Rough mathematics can be done with less resources and save greenhouse gas emissions. It's a bit of a sweeping generalization, but if you build a computer that, say, calculates something to 20 decimal places, it needs a lot more circuitry, which is power hungry, than a computer that, say, calculates things to 3 decimal places. And that could save 20–30% of our costs on training a model if we decided that we're actually going to just do everything in a kind of a rather rough approximation. And in fact, one of the things that's a very hot topic in this day and age is mixed precision calculations, because it's quite possible to ask a computer to use very, very imprecise but quick mathematics to solve a problem and get you into the ballpark. You haven't quite got to your answer, but you got close to your answer. Then you can switch. You could switch to a high precision calculation to really work out what the correct answer is. But by doing this, you can use less resources on the computers. It's very good for greenhouse gas emissions. So without further ado, let's get into the algorithm that Hero wrote about for us. So in order to do that, I've got for us, there we are, an example in Desmos, which I will just bring in here. We used Desmos on the previous version of this course, and I really love it, as I think I told you. So what I've got here, I think, this will allow us to sort of really get in it and kind of understand. So I've got a chart here, I've got my axes, and then this blue line that you see here is actually the chart of y is equal to the square root of x. When you ask a calculator or a computer to calculate the square root, it always gives you the positive number. There's actually 2 numbers. I mean, I've given an example here. I think you can see this line here is at 25, and I go up and intersect, and it comes across here, and it's actually against 5. The square root of 25 is 5. We all know that. But equally, minus 5 works. A minus times a minus is a plus. Minus 5 squared is 25. Minus 5 is a possible solution. But computers tend to just want to give you one answer, and that's why the chart looks like this. But another way of visualizing this, I could just square both sides of this equation. So y squared is equal to x. And if I swap now x and y, so let me call that x becomes y, and on this side this becomes x squared. In other words, y equals x squared. Essentially it's the same. I've just swapped the x and the y. What that means is kind of we switch the axes. It's probably a bit easier for us to work with that type of equation. So I'm going to do that. I'll bring that equation up and let me get rid of that equation. And I'll move this over so I'm not standing and blocking it. So here we can see that, if we took a value on the x-axis and we took an interception, we could see that there's a positive value but a negative value as well. Against everywhere where there's a positive value, there's a negative value, which is exactly what we know to be the case. You get a positive and negative values. To explain the Hero's method, I'm going to use it to find the square root of 81. We all know the answer. It's 9 or minus 9. And to make things simpler, I'm going to plot, let me see if I can select that. There we are. So this is now y equals x squared minus 81. So I have to zoom out quite a long way for us to see that. So down here we've got 81, and there's an intersection. There's an intersection with the x-axis here and here, and those are the answers that we are kind of looking for. So if I kind of zoom in, I can see it's very close to minus 10 and plus 10. We know really that it's actually, that must be crossing, hopefully, if it all works out. at the point 9 and minus 9. So this is basically, let me just clean up my board here. I'll show you the thought process that Hero went through to make this all work. So what I've got here on the chart is the graph of, as I explained, x squared minus 81 is equal to 0. And where the roots of that equation are what we want to find. It's the square root of 81. If I put 9 in, 9 nines are 81, minus 81 gives us 0. And it's this point and this point here where it actually intersects that axis. But just playing around with this, Hero thought, well, actually, I could kind of do some manipulation on this. And as we do in algebra, we can, as long as we do the same thing on both sides of the equation, we can mess around with it. So I'm going to divide by x. Well, x squared divided by x is just x. And here, 81 divided by x is, I'll just write it as 81 divided by x. And 0 divided by x is 0. So that's another way of looking at it. It actually looks quite different when we plot it. So let me do that for you. So now I have, let me also take away that original one. I'll see if I can, there we are, zoom in a little bit. It is exactly the same problem, stated slightly differently. You can see that it still has roots at minus 9 and plus 9, although it's a bit hard for us to see at this scale. But now we've got these rather sort of beautiful, curved, sweeping lines that, you know, the way they follow. But Hero then continued looking at this and he thought, well, okay, the other way now, what we could do is we could say, we could add 81 over x to both sides, which means on this side we just get x, and on this side 0 plus 81 over x is 81 over x. I've just moved it around, put it all on one side. This can be split into two. We could consider the graph of y equals x, and we could plot the graph of y is equal to 81 over x. And if we plot those two graphs, where these y's match, in other words, where the two lines intersect, will give us the solution. So this was the way that Hero said was the best way for us to look at this equation. So without further ado, let's do that. If I click here on separate, right, it's looking a bit more funky now. I'll clean up and then we'll come back to that and we'll have a little look and see what it is that that shows us and what Hero was kind of thinking about when he did that. Right, so I think it's probably easier if I take away my previous version and I'll try and get out of the way a little bit. We can see now that instead of the roots being on the x-axis, it's where the two lines meet. The curved line is 81 divided by x, and then we've got just y equals x. And where they join, this is the point minus 9, minus 9, and here is the point 9 and 9. So it's giving us the solutions, but in slightly different way. It's at the intersection of two lines. Now, if I click here, I'm going to just say focus on the positives, just like the calculators and the computers like to give us the positive numbers. I'll do that. I'm going to just sort of do this. So here's my example. the example that Hero sort of looked at. In fact, I think I'm going to try and maybe if I can get a bit more space there, I'll sort of try and zoom in. Okay, that looks good to me. I'm going to bring up here, if I click here, I've got a little gadget that I can, excuse me, I don't want that on yet, basically move around. And it only moves to integers, so I can pick numbers and I can move around here. And that allows me to sort of explain the thought process that Hero went through. And Hero realized that with this kind of chart, there are really 3 zones. When our little control is over on the left-hand side, the curved line is always above the straight line. And the opposite's true. If we go across to the right-hand side, the straight line is now always above the curved line. And there is a third case, which is when we actually put our marker on the answer, 9 in this case, where the 2 points actually intersect. Obviously, they're in the same place. But the other thing that we can kind of see is very much the case. Where the real answer lies is always between the bottom and the top. Whether we're on this side or whether we're on this side, these go out a lot further, but the point that we're looking for is always between them. So bingo, there was Hero's answer. Very easy way for us to find a square root is basically we can look for, I'll bring up this guideline. So there's an example of a guideline where actually Desmos is finding the midpoint. It's not quite the midpoint because I've asked it to do everything in whole, round, integral numbers. So it won't put at a 0.5 or a 0.25. At the moment, what I'm doing is rounding everything to the nearest integer. But it's, apart from that rounding, it's always picking a guide that is in the middle between the bottom and the top markers. Then, for us to work out the answer, it's pretty straightforward. So, I mean, you can see, I'll need to sort of zoom in a bit here. Let me suppose that I start off with a guess, which is 2. You can see the guide is saying, okay, I reckon 21 is a better guess. How did it get that? It says, I know there's a bottom number, I know there's a top button number, and I know that anywhere in between is a better guess. So it plumps the middle and says, right, let's go to 21. So I'll obey it. I will go to 21. Okay, there we are. I've moved it to 21. The same thing. We know a better guess is somewhere in the middle. It's suggesting 12. If I move now to 12, it's now saying, okay, in the middle. So I suggest 9. I move to 9. It still says 9. It can't get a better guess. Of course not, because we've got to the solution of exactly what we wanted. So this is a great example of, well, back in the day it wasn't machine learning because the calculations had to be done by hand. There were no computing machines. But this is how machine learning works. You start with a guess and you have a process, and we'll talk about the processes, things like the backpropagation algorithms and gradient descents and all these fantastic things in modern day mathematics for machine learning. But this is the way it works. It just says there's a recipe that tells you, you've got to guess where's a better solution. what's the direction that we need to walk in. So that's my first point. Now you remember my second point was about rough mathematics and saving greenhouse gases. Now to really illustrate that point, I hope, let me try and select this here. So I'm going to deselect these guides that are in the middle, and you see I've got here something that says guides random. So guides random on this, perhaps I should try and change the view. What this will now do, it calculates the top and bottom. That actually looks pretty much like the sort of guide we had before, but the random guide, you see there, is right next to the bottom. What it's actually doing, now this, let's see here, that iteration is right down the bottom. So instead of it picking the midpoint, it simply picks at random anywhere along that line. Now, it doesn't get much rougher than that, the mathematics, because we're actually putting in no precision. There, that was a good one, look at that. So it basically said, okay, you've taken a choice, but I'm going to give you a next choice, which is hardly any movement at all, because it picked one that was, you know, right at the top. But does this work? Does this actually work? Well, yeah, heck yeah, it does work, and you know we can show that. So without further ado, so I've picked 25 here, and the system has said a better guess is 24. Any number is a better guess, basically. So now it's picked at random 14. So I will obey. I'm going to move to 14. And now, as luck would have it, that was good, wasn't it? It's picked 9, actually. It's picked the answer directly, so I can go straight to 9. Let me try that again. Actually, Desmos has got a thing where you can reshuffle random numbers. You see, I can do this, and it kind of reshuffles. We'll stop at 1. So my initial guess is 3, and it's saying go to 23. So I will go to 23. It's now saying go to 15. I'll go to 15. It's suggesting that we move to 12. I'll move to 12. Oh, it's just undercut. It says go to 8. So I will go to 8, and now it's saying go to 9. So I go to 9, bingo. There we are. It's brought me back to my solution. This kind of roughness, I'm just picking a number out of a hat. As long as it's between the top and the bottom, it doesn't matter. I've shown you that it works. It actually gets us to a solution. It will bring us to the square root of 81 that we wanted. Now, this kind of approach really came to the fore with Google were working on some training of large language models and other models, and they had a department called Google Brain, and they suggested that computers should use really rough estimates of numbers, and the way it worked is computers will often calculate things to a standard is something like 15 decimal places, but what they suggested was each number would take a lot less memory, and the computer would only calculate it to, let's say, 3 decimal places, or 3 significant digits. So the nearest it could get to a number like pi would be 3.14. And we all know, well, there's infinitely number of digits, but even on a handheld calculator, when you press pi, it will write lots and lots and lots of digits. But Google Brain published this as a new numeric standard, and I believe it's called Brain Float is the standard, and it is very much used today. It gets you to the answer when you're training really quite quickly. Now, there's no reason why you can't use very rough mathematics to start off with a pure guess and to train a model to get it to the ballpark. to get near to a solution. And then you could switch to a high precision type of mathematics to really get the correct answer. The fact is that by doing that, you'll have spent a great deal of the training time using this low precision, and that a computer can do faster, so it gets there quicker, saving resources, but it can do it with less memory and fewer transistors at the end of the day. It's really quite basic. So that's basically those two messages that I wanted to say. So what have we learned? There's nothing new. ML and AI, you could say, was invented 2,000 years ago by a hero. If we could wake him up, bring him back today, time travel, and explain what we're doing with machine learning, I think he'd get it. He'd absolutely understand it. If we talked about the advantages of using these lower precision calculations to get to the answer quicker, I think he'd absolutely appreciate that. So it's very interesting that the mathematics behind machine learning and AI is really quite simple, quite old, yeah, by using very low precision, we can save resources. So that's my sort of learning and message for today. I hope you've enjoyed it. On the next one, I want to talk a little bit about gradients, because we need to get into that. And that's leading us into the work of Sir Isaac Newton. More history, I'm afraid, but a lot of the work that Sir Isaac Newton did, highly relevant to today's machine learning. And I think it's well worth revisiting some of his work and putting it into the context of ML. So that'll be coming very soon, and I hope you enjoy it. But thank you for joining me today, and goodbye.